guys, welcome back to my math YouTube channel. Today I'm back here with another method for integration or integrating functions, and especially here we will be integrating rational functions where we have a numerator and a denominator. And the method that we are going to use here is called the method of partial fractions, or sometimes we also like to call it as the partial decomposition. So guys, I'm going to illustrate this method with some examples, and then we're going to try to actually do some or evaluate some integrals of this type where we have rational functions. And the other thing that I have to let you know is that you will see when I start writing these examples, we will realize that we cannot use the other methods that we have learned so far, or you have learned them on your own, on those functions, on those rational functions. So one has to use something different, something new. Guys, again, if there are rational functions or other types of functions where you can use other methods to evaluate the integral, one has to use those methods. But when those methods don't work, then one has to use something called the method of partial fractions. In this section, guys, there's going to be three types, and I will show you those three types, and I will illustrate this by a general form and then also with examples. So guys, let us start with the first general form for a partial decomposition or partial fractions, and then we will try to understand that with that example. So guys, the partial fraction type 1, so let us start with type 1. In type 1, guys, if we have a polynomial function as a rational function, let us say we have a polynomial function divided by another function, because we are looking at rational functions here. And let's say the denominator has distinct linear factors, and that is type 1, because in the other type it is going to be slightly different. So in this case, we have a polynomial function upstairs, and then downstairs in the denominator we have maybe, let us say, n different distinct linear factors. So guys, that is very important. So let us say those linear factors look like this: a1x plus b1, and then the other one is a2x plus b2, and so on to, like, let us say an. So guys, here I'm writing the formula for a general case, and then we are going to use this and apply it to some actual examples. And then let us say this is anx plus bn. So if we have something like this, then this can be written out into different pieces, and that is the whole idea of using the partial decomposition. If I have a polynomial or a rational function in this form, then we can break it down into several pieces. And why do we want to break it down into several pieces? Guys, since the goal is to actually integrate, we want to integrate a rational function. We cannot directly integrate a rational function which is given or written in this form. So that's why one has to decompose it, or one has to break it into several pieces, and then one can use some rules or techniques that we have learned prior and apply those to actually evaluate the integrals. So that is why we are trying to decompose or use this method called the method of partial fractions. So in this case, this is going to be equal to constant c1 over a1x plus b1 plus another constant c2 over a2x plus b2, and so on to so forth, and finally cn over anx plus bn. Guys, there is a condition here, and that condition is very important. There's two things. So number one is I'm going to write this here. Number one is that the degree of the numerator has to be less than the degree of the denominator, and let us call this as q of x. The degree of the numerator has to be less than the degree of the denominator. This decomposition or this formula is only going to work if the degree of this numerator, that is the highest power of this, is less than the highest power of the denominator, and this will make more sense. And even this whole formula or this whole general statement will make more sense when we actually look at some concrete examples. Okay, but guys, I first wanted to write the general form for type 1, where we have something, a rational function of the form where the denominator can be written as a product of linear factors. Guys, that is important. The second step, second key thing here is that the denominator can be written in or as linear factors. Can be written as linear, or maybe, you know what, I should even add one more keyword, and that is very important as well. Distinct linear factors. And guys, I would like you guys to think about these things. Why is it only working for just distinct linear factors? Why it does not work for quadratic factors or factors that are repeating and things like that? Guys, that is something I would like you guys to think about. Of course, I'm going to show you examples that might also give you some ideas or hints about like why it works for only distinct linear factors in the denominator. And also the degree of the numerator has to be less than the degree of the denominator. So guys, these are the two key things that one has to keep in mind before one starts to actually write the partial fractions or partial decompositions. Keeping this in mind, guys, now I'm going to get rid of this so that we have space to actually look at some examples. But guys, if you like are taking notes on this, please make sure you write this form in your notebook somewhere. Or if you are not taking notes, then you can also find this form in your calculus textbooks. Okay, so this is the form that we're going to use in type 1. And now let us actually use it or apply it to a particular example. It will make more sense when we actually apply it to an example. So I'm going to apply it to an example, and then we are going to actually try to do the integrals or evaluate the integral of that function. So this is type 1. This was the general form. Let's see an example now. So guys, the example that I have here is, and I'll call it example 1 in the partial fraction world. We want to integrate a rational function of this form, x plus 2 in the numerator divided by x squared minus 4x plus 3, and with respect to, of course, with respect to dx. Okay, so guys, first step is again to go back and think about like other methods, whether it's the substitution method, whether it's the clever substitution involving trig functions, or it is the integration by parts method, or just straight away basic identities that one can use. So if we think about all those methods and then try to apply those to this particular rational function, they're not going to work. They're not going to help us, or they're not going to help us to actually evaluate this integral. So that's the reason why one has to go on and try to figure out some other methods, and the other method is the method of partial fractions. Okay, so how can we use partial fractions to actually evaluate this integral? The idea is to break it down into different pieces, and to especially break it down into pieces that we can easily evaluate the integrals for. And if we can, if we are able to accomplish that, then we will be able to actually evaluate the integral of this function. So guys, in order to do that, I just showed you like the general form, and let us see if this linear function actually qualifies for that general form. Number one, guys, the degree of the numerator. The degree of the numerator is 1, and the degree of the denominator is 2. So the first point is checked, right, which it satisfies that first condition. And the second condition is to see that the denominator can be written or has distinct linear factors. That is something one has to still verify for this case. So let us go ahead and verify that, and if it qualifies or if it verifies both of those, then we can break it down like we wrote the general form. So I'm going to take it on the side. So let us do the work right here. I don't have like so much space here, so I'm going to bring it here. So I'm just going to bring the integrand, this piece. And the first step I'm going to do is I'm going to try to write the factors for the denominator. That is the only way I can figure out whether I have distinct linear factors or I don't have factors at all, or what is going on. So this is x plus 2, and then downstairs, let us see if we can write the factors. Let us try. So we got x here, and then we want to come up with two factors of 3 that add up to -4. right? Two factors of 3 that add up to -4. How about -3 and -1? -3 times -1 is +3. -3 plus -1 is -4. So I think we have two factors. We can write the denominator as a product of two factors, and in this case there are two distinct linear factors, as you can already see here. So that means this qualifies for the type 1, and now we should be able to kind of write the partial decomposition for this rational function. So let us use that general rule and write the partial decomposition. So guys, using that rule, this can be written as the sum. So here we have only two factors, so there's only going to be two terms. Guys, remember in the general form downstairs or in the denominator we had n terms, so we could break it down into n terms as well. Here I have two factors, so we are going to break it down into two terms. So we can write this as a over x minus 3. That is how we break it down. If you remember the formula, there was a c1 and c2, those were all constants, right? So I mean, instead of using c's, I'm going to use a and b. So a over x minus 3, and then I can write b over x minus 1. Guys, if you want to use c1 and c2 and c3, that is totally fine. They're constants, and we have to find the value of those constants. So you can denote them by a's, b's, c's. It does not really matter. Okay. So guys, this is the partial decomposition, and once we have the values for a and b, then we can bring it back here because we just have the same rational function broken down into two pieces, and then one can easily evaluate the integrals for this piece and this piece, combine them. That would be the integral for this particular rational function. Okay, so the idea is to, when we have something like this which we cannot evaluate using the other methods, one has to break it down using the partial decomposition method, which we're able to do by using the general form, and because it also satisfies both the criteria here. Now guys, before we move on to evaluate the integral and use the formulas or anything, identities that we know, we have to evaluate this a and b. So a lot of the work in this, using this technique, is all about finding those constants, whether it's just two constants or more. In this case, it's two constants. So let us see how we can evaluate this. Again, there are a few different ways. I'm going to share with you one of the ways which I feel is easier and convenient and even faster. And if you have any other method of doing it, guys, I also know there's another method which I used to use when I was learning it in college and in high school, but now I learned a new method and I like the new method over that previous method. So what we do here is, guys, let us now just focus on this particular box, and our goal is to first evaluate the value for a and the value for b. Okay, so what we can do is we are going to get rid of this denominators. Okay, to get rid of the denominators, what we can do is we can multiply both sides by this whole thing, whatever is in the denominator here on the left hand side. So guys, think about it. If I multiply both sides, left hand side with this and then right hand side, what I'm gonna get is this. On the left hand side, if I'm multiplying by this whole thing, this is going to cross out because I'm multiplying by exactly the same thing. So it will cross out. I will be left with only x plus 2 on the left hand side because I'm multiplying by this guy, right? On the right hand side, I'm multiplying by the same thing, but I have to multiply the first rational function as well as the other rational function. When I multiply this guy with this, x minus 3 and x minus 3 is going to cross out, and I will be left with only a times x minus 1. A times x minus 1. Okay, because x minus 3 and x minus 3 crosses out, there's only x minus 1 left here. Then plus, then again, guys, when I multiply the same thing to this rational function, because we have to multiply to the both sides, on this side it just goes away. I'm only left with x plus 2. On the right hand side, I have two rational functions, or two terms. So I got to multiply to the first term. When I multiply to the first term, x minus 3 and x minus 3 crosses out. I'm left with only x minus 1. And when I also have to multiply to the second term. And when I multiply to the second term, in this case, x minus 1 and x minus 1 crosses out, and I will be left with b times x minus 3. Okay. That is step number 1. Once we have it decomposed into two pieces, that is what we like to do. Now from here, keep in mind, the goal is to solve for a and b. There's few ways now to solve for a and b. The easiest way is to, guys, think about the method of elimination or isolation. You isolate one of the variables, solve for the other one, and then you solve for the other one, isolate the first one. So guys, what we can do here is, What I'm going to do is, let us try to isolate B first and solve for A. Most of the times we will be able to isolate one and solve for the other. If there are times when we cannot do that, then one has to set up equations and do some extra work. And we may have to do this in some other types. And once we get to those types, I'm going to show you those examples as well. But in this case, things are going to work out nice and easy. So I'm going to say let x equals to 3. And why did I choose x equals to 3? I could have chosen any value for x, guys, because for this equation, I don't have any specific values that satisfy x. So I could have chosen anything. But guys, the reason why I chose x equals to 3, if I look at this guy right here, 3 minus 3 becomes 0. 0 times b becomes 0. That means I have already isolated b, or I have eliminated b, and I can solve for a. That is the reason why I used x equal to 3. So let us apply x equal to 3. If I set x equal to 3 here, 3 plus 2 is 5. Here, 3 minus 1 is 2, so it is twice a. And guys, this is going to be plus 0. I don't have to even write it or worry about it. Guys, I have this simple equation. Can I solve for a? Yes, we can easily solve for a by dividing both sides by 2. So if I divide both sides by 2, I get a equals to 5 halves. That is good. We already got the value for a. So now we can go back and substitute that value for a here. But what we need now is the value for b. To find the value for b, guys, what do you think we can do? So to get the value for b, we want to isolate this a term, right? And again, this is not the only way of finding a and b. There's other ways as well, guys, but I find this way easier and convenient, okay? So to get rid of the a value, or sorry, this whole term, if I set x equal to 1, what's going to happen? 1 minus 1 is 0, 0 times a is 0, so the a terms, this term vanishes. I will have term in terms of b. I will have some number on the left hand side, and we can solve for b. So guys, that is the technique, that is the method to finding a and b, or any constant for that matter. So let us do that. Substitute x equal to 1, so it will be 3. On the right hand side, this vanishes, becomes 0. Here I have 1 minus 3, which is negative 2b. We can easily find the value for b, which would be negative 3 halves. We have a, we have b. So let us go back and let me first rewrite this. So we can rewrite this as a over x minus 3. I have the value for a. So it is 5 halves. And then I have x minus 3. Guys, keep in mind that 2 can be written with just x minus 3. Okay, please don't get confused with that. I could have just written 5 halves and then divided by x minus 3. But if I simplify that, it would simply be 5 over 2 times x minus 3. And then I will put a dx with it. Plus, there's a plus here. Then another integral. And now I have to get rid of some stuff so that we can finally compute the whole integral. So I'm going to get rid of this, and then I will have to get rid of some more stuff here. So the second one is going to be minus 3 halves, so minus 3 over 2, and then I have x minus 1. Of course, I have a dx. Guys, again, we started with this rational function. We broke it into 2 pieces, but with these 2 pieces, I have an a and b, which are constants. We don't know the value for those. Then we tried to use some algebraic techniques to set this thing up like this as an equation. We use another technique to find the value for a and b. We found the value for a and b. We substituted it back in this partial fraction decomposition. I have this, I go back, and now I'm trying to evaluate the integral, because the goal was to break it down. We broke it down into 2 pieces. Now we should try to find the integral and see if we can find the integral using the formulas, identities, methods that we already know. Okay, so I have to get rid of this. We're very close to actually evaluating the integral. Let us see what we have here. So what I'm going to do here is, guys, 5 halves, we can already take it outside, and then I have integral of 1 over x minus 3 dx. And same thing here, I'm going to take out the constant, which is negative 3 halves. That's what we do with the constants, right? Take those outside the integral sign, and 1 over x minus 1 dx. So we're almost done, guys. This is 5 halves. We know the integral of 1 over x. We know the integral of 1 over x dx, or integral of an inverse function, is just log of that function. right? In this case, this is very similar to this, but it is more like of the form ax plus b. If you have already watched my videos, prior videos, guys, it is very similar to this. All you have to do is, this is equivalent to ln of ax plus b. I have actually talked about this in a video which talks about the shortcut methods of integrating functions of the form ax plus b. And we all know that ax plus b is the linear form, okay? And we have log of ax plus b, but we have to divide by the derivative of the inner or the coefficient of this x, whichever you like to, however you like to think. I usually like to think this as dividing by the derivative of the inner, which is a. Guys, this is just on the side, just I'm trying to remind you what we're going to use here. So this function, this first function and the second function both qualify for this formula, right? They look like this form. So it's going to be ln of x minus 3 divided by the derivative of, or coefficient of x. It is 1, so you don't have to even worry about it, or you don't have to write it. Then minus 3 halves, and the same thing here, ln of x minus 1, don't forget, plus c. Guys, there we have the final integral for this function, which could not have been done by using the other techniques that we have learned so far. So one had to use the method of partial fractions. It's a new technique, a new method that helps us to finally evaluate the integral. Okay, so guys, this is type 1 and example 1. I'm also going to show you some other types in this partial fraction world, so try to practice this one. I will see you next time with another video and another type, and we'll look at some examples as well.